Let's get started. Hi, everyone. Welcome to the 16th ECS and Cloud Feedback Virtual Symposium. Today, we're back to the traditional format. We have 3 AGU-style talks, each 12 minutes. There'll be about 3 minutes for questions at the end of each talk, and then we'll have a sort of short general Q&A discussion at the end. If you have any questions or comments, you can feel free to type them into the chat, or if you'd prefer to ask them live, just raise your hand and then we'll unmute you. We're always looking for more talks, so if you have an idea for a talk for a future symposium, please reach out to anyone from our executive committee. You can find our contact information as well as a lot more like videos of past talks and the sign up for a mailing list at our website, which you can see here. And with that, we will move on to our first talk. So our first speaker is going to be Jonathan Gregory. He's a senior scientist at the National Center for Atmospheric Science, located at the University of Reading. And he's a Met Office Science Fellow at the Hadley Center in Exeter. He's going to be discussing a new conceptual model of ocean heat uptake and transient climate response. Jonathan, why don't you share your screen when you are ready?
Thank you, Jonah. Thank you thank you to all of you for inviting me to speak. I would like to talk about this piece of work, which has been going on for a number of years with various collaborators. It's not published yet, but there is a paper which is complete, and I hope it will be submitted very shortly in coming weeks. And it mostly concerns ocean heat uptake efficiency, but it also touches on transient climate response. So the issue is the energy balance framework that we're used to thinking about, which is very commonly represented as 2 layers, 2 global average layers. So the net downward heat flux, N, is the difference between the applied forcing, F, and the climate response, alpha T, where I've defined alpha as a positive number. So a larger alpha means a smaller equilibrium climate sensitivity. And the difference between those is also the rate of ocean heat uptake, since on decadal timescales, the atmosphere has negligible heat capacity. And that is mostly, in the 2-layer model, that is mostly a term which is modeled as gamma times T minus TD, where T and TD are the differences from equilibrium of the upper and lower ocean temperatures. And gamma is the thermal coupling. So this model's been fitted to many OGCMs. In Geoffroy et al. Fitting of CMIP5 models, alpha is 1 plus and minus something, gamma is 0.7 plus and minus something. Both of these are AOGCM specific numbers. And with these numbers, you can reproduce abrupt 4 CO2 and 1% CO2 quite well. Now, most of the heat capacity is in the lower layer and very little in the upper layer. So we can make a further approximation of just ignoring the upper layer heat capacity and allowing the lower one to be infinite. If the lower layer is infinitely has an infinite heat capacity, then it never warms up. So you can also neglect TD. And with that approximation, we can replace the coupling with just kappa T, where kappa is the ocean heat uptake efficiency. So this is an approximation. In fact, kappa tends to decline because the deeper ocean does warm up. But that's if you like, a second order effect. So we to a reasonable degree of accuracy, we can ignore that. And that gives us this really simple representation of the global ocean heat uptake balance, where F is instantaneously balanced by some heat which is being lost to space, alpha T, and some into the deep ocean, kappa T, where the surface T of the upper ocean, that is the global mean surface temperature change from equilibrium. So then that T is, at any given time, F divided by alpha plus kappa. So that gives us a simple formula for the TCR, for example. That is the forcing at the time of doubled CO2 divided by alpha plus kappa. And in addition, the rate of heat uptake is N is KT. So that's N is K times what I just said before. And that number, N, therefore, is larger for larger kappa, because the kappa in the numerator is more important than the denominator. So we've got this idea of ocean heat uptake being determined by this thermal coupling between the 2 layers. And if that kappa is bigger, so will heat uptake be bigger. Now, the two-layer model doesn't tell us anything about what kappa should be, but AOGCM analyses tell us that kappa, that is n over t, is in fact linearly related to the control strength of the AMOC. And that's a very good relationship. And so until I tell you again, I'm talking about the 2 times CO2 state, that is year 70, under 1% CO2. And what I've plotted here are a mixture of CMIP 5 models, which are the capital letters, and CMIP 6, which are lowercase letters. So you might think that a bigger ocean heat uptake efficiency with a stronger AMOC is because the AMOC itself is taking up heat. And that is suggested by, for example, looking at a cross section like this, which shows us in the stream function, the sinking branch of the AMOC in the North Atlantic. That might be carrying heat downwards. But on the other hand, this idea is a bit surprising because most heat uptake is actually in the Southern Ocean, not in the North Atlantic. So if we already seen that n should be larger for larger kappa, and now we see that kappa is larger for stronger AMOC, putting those two things together means that the two-layer model predicts that n, and therefore the ocean heat uptake, which is the time integral of n, should be larger for stronger AMOC. But actually that's not true. So the right-hand plot here is a scatter plot of the amount of heat that's been taken up by year 70 against the control AMOC, and you see there is not a significant correlation. So to try and explain this, this contradiction of the two-layer model, we propose a more elaborate version, which we call MT2. And it's called that because in this model, n depends not only on t, but also on the control AMOC strength, for which we use the symbol m. And the 2 is for the two-layer model, which I'll get back to. So in this model, n's got two contributions, nt and nm. The nt part is still forced by the temperature, like in the two-layer model, where q now appears instead of kappa. And the other part is a direct uptake of part of the forcing into the deep ocean without causing surface temperature change. And this part is linearly related to the AMOC. So the AMOC here is expressed as AMOC strength in the control is expressed as m minus m0. So now there are two specific model-specific variables in this conceptual model. They are alpha and m, whereas q, s, and m0, which is minus 10 spare drops, are all AOGCM independent constants. So whereas before we had an AOGCM specific kappa, now we have an AOGCM specific m instead, and q is a universal constant. I can't tell you exactly what is the physical reason for this model working, but we have some other evidence that suggests an interpretation. So this interpretation is that the NT part, the temperature forced part, is what occurs at low latitudes principally, and that is suggested by this correlation across AOGCMs between the global mean rate of ocean heat uptake, and actually that should say N and not NT, sorry, and the local SST. So what this is telling us is that models which take up more heat are those models which warm more at low latitudes. So it's reasonable to suggest that that's where the climate sensitivity matters. And if the climate sensitivity dictates that there will be a large temperature change at low latitudes, which in fact dominates global mean temperature, then that gives a larger amount of heat uptake. You see that the correlation is negative at high latitudes for this quantity, and that's because in those models, there's a lot of heat taken up, and the fact that heat is taken up means that the surface is cooler. So the process is different at high latitudes. There's less warming because heat has been taken up efficiently. So that's not the NT part. The NT part is the low latitude part. The high latitude part is the NM part. NM represents a high latitude heat uptake, which occurs with small local SST and rather small contribution to the global mean temperature change. And this is revealed by a correlation across models of the uptake of a passive tracer that was done in FAFNIP. So a passive tracer was added to the ocean with the same distribution as heat being added under CO2. And correlating across models, there's a strong correlation between where this passive tracer goes, which is the same in total in all models, and the AMOC strength. And you can see that models with stronger AMOC tend to remove the passive tracer from the surface, especially in the Southern Ocean, and store it more underneath. So they are taking up heat more efficiently in that sense. So this leads to a correlation at the surface. You can see that at the surface, it's always an anti-correlation. So if we actually look at the surface, we see that SST warms less in models with a stronger control AMOC. And the right-hand plot is a correlation of the warming with depth. So that's like, if you like, the mean overall latitudes of the plot I showed before, showing that there is more heating at depth below 500 meters in models with a stronger AMOC and less at the surface. So now putting these facts together, just before I go on to that, so this on the right, on the left here is an expression, another expression of that, the fact that you can see everywhere in the world, the surface warms less in models with a stronger AMOC, control AMOC. That means that there is an anti-correlation across models between TCR, the global mean warming at the time of doubled CO2, and the control AMOC. And on the right, you can see that there is also an anti-correlation, a correlation between alpha and AMOC. That is, there is an anti-correlation between effective climate sensitivity and control AMOC strength. Okay, now we put these things together to explain what we set out to explain. In this plot here, the letters represent the diagnosed ocean heat uptake efficiency from GCMs, and you can see again the correlation between the ocean heat uptake efficiency and the AMOC. The blue crosses represent the predictions of the MT model for kappa, and you see the blue crosses are pretty close to black letters, so it's a fairly good prediction. And the formula that's being evaluated is shown on the right. So it's got these two terms, NM and NT, both divided by T. Now we see dividing by T that we just have Q for the NT part, and Q is a universal constant. So that is not contributing to the spread of kappa. It's S delta M, which is. And now we see that the explanation, part of the explanation for models with a stronger kappa having a bigger AMOC, the stronger AMOC having a bigger kappa, is that delta M in the numerator. They are taking up heat more efficiently. But in addition to that, as we've seen, those models also have less global warming, so the denominator is smaller. So kappa is bigger in models with a stronger AMOC, both because the heat is being removed from the surface more efficiently, and therefore the surface is cooler. But there's also this effect by alpha, and in fact these two effects are separate, which can be shown here. So here the red line is a recalculation of what the ocean heat uptake efficiency would be using the model average alpha, the model average effective climate sensitivity, so removing that factor. And you see there is still a correlation between AMOC and the ocean heat uptake efficiency. So that shows that both the factors contribute. The ocean heat uptake efficiency is bigger in models with stronger AMOC, both because of a more efficient removal of heat from the surface, and because those models have a lower heat capacity, a lower effective climate sensitivity. And both of those things cause a smaller T. But for N themselves, these two effects are opposed. So models which have a higher climate sensitivity have a higher T, but those are also the ones with a smaller delta M, So the NM and the NT charts, which act together in the ocean heat uptake efficiency, are opposed to each other in N. And that explains why there isn't a correlation between the amount of heat taken up and the AMOC, although there is a correlation with the ocean heat uptake efficiency. Okay, so I shall probably have to skip to the end now, but I can just tell you the generalization of MT2. So as I said, I was just talking about the doubled CO2 state in 1% CO2 up to now, but of course, we want to know, does this work more generally? So we've also tested it for all times in 1% CO2 and also for abrupt for CO2. And the generalization is that the S term, the NM term, has the form of a universal constant times the forcing, where the constant is about 0.5% per Sverdrup. So a certain amount of the forcing is removed from the surface by this term, and the amount of it depends on how strong the control AMOC is. So you can also express it in the second way here. NM is some constant, which is a model-specific constant, times the forcing, where that constant is about 15% plus or minus something, depending on how strong the control AMOC is. So therefore, in abrupt for CO2, where the forcing is constant, NM is constant, whereas in 1% CO2, both NM and the forcing go up linearly with time. And then the other parts, QT, the temperature division dependent part, nt over t. The value of q isn't constant in time, but it is independent of models. It can be predicted by a two-layer model with AOGCM independent parameters, given the AOGCMs all have a constant, a fairly similar temperature profile. So if you take the AOGCM mean temperature profile in 1% CO2, you can predict what this Q will do. Okay, so let me skip the other consequences and go on to the conclusions. So to summarize, the MT2 model is an elaborated version of the very familiar two-layer model, which has an extra term. So the original two-layer term is NT, and NM is some fraction of the forcing, which is another way by which forcing can get into the deep ocean, and it doesn't cause global mean temperature change. So the NM term is a model-dependent fraction of the forcing, and that term we think represents high latitude uptake of added heat as though it were a passive tracer with little effect on surface temperature. Whereas the MT is the low latitude uptake, which behaves like the familiar two-layer model, and that term enters the energy budget with alpha. Ocean heat uptake efficiency N over T is correlated with M because TCR is smaller in AOGCMs with larger M, and that is in turn because of larger more efficient passive tracer uptake, mainly in the Southern Ocean, and smaller effective climate sensitivity. But because these two terms are anti-correlated, ocean heat uptake doesn't depend on this control AMOC strength, just the efficiency of it does. And this is something I didn't show you, but it is another consequence of the model that the AOGCM spread of TCR comes mostly from alpha at all times. And that, I think, is the explanation of the finding of gross, that it's somehow kind of surprising that the effective climate sensitivity is a better predictor at the warming, say at 4 CO2 under 1% CO2. But I think this the MT model framework helps to account for that. That's it. Thank you.
Thanks so much a lot for everyone to chew on. Are there any questions for Jonathan? Lily, do you want to unmute yourself?
Sure, yeah, I was just curious, so this focuses on the role of the control AMOC, and I was curious since that's also correlated with the AMOC decline under forcing, if you also looked at the role for the AMOC decline or the relative roles of those two.
Yeah, that's a good question, of course. As you know, AMOC decline is at 1% CO2 is proportional to the control AMOC across models. So just from a correlation, one couldn't tell which it was, whether it was the AMOC decline or the AMOC control strength that matters. But I think there's various evidence that's the control strength, and maybe the strongest evidence is that you still get this correlation in the passive tracer uptake experiment, where there is no climate change and the AMOC is not weakening, but you still get the same effect. And I don't think that the climate sensitivity part, the alpha part, is related to the weakening of the AMOC, because it isn't an effect that appears specifically in the Atlantic. As you saw, it's it's all over the place. It's particularly a tropical effect, but certainly not in the Atlantic or the North Atlantic specifically.
Okay, Christy?
Hi, Jonathan. Very nice talk. Could you go to slide 11?
Which one's that, Christy? Tell me when I get there.
That you have a counter at the top. So this is 8, 9.
Oh,
more.
there. Ah, right. Thank you. Yes.
Yeah.
Okay, slide 11. Fine. Mm-hmm.
So in this equation, F and T are anomalies relative to pre-industrial.
That's right.
So if you set F and T to 0,
yeah,
you're still left with this NM term.
That's right.
So I'm trying to wrap my head around that, because it seems like in that case, you don't actually have zero energy balance.
Well, that's a good way of putting it. Yeah. So in fact, initially, we kind of discovered this term by plotting against T and extrapolating back to T equals 0. And it does seem to imply that you could contrive a model which had no temperature change, but still had heat uptake. But that is sort of consistent with this term here, because temperature actually looks somewhat like that. So what could be going on if you could contrive such a model is that it just had a very, very low latitude climate sensitivity, if you like. So it didn't warm up at all at low latitudes, but yet at high latitudes, some of the forcing is added to the surface, and because of wind-driven overturning, that added heat is swept away straight away and causes very little local warming. And since that's not much of the global mean temperature anyway, the global mean temperature change is small. So I think it could be understood in that way. Does that make sense to you?
Sort of. I'll have to wrap my head around it.
Yeah.
Because it suggests if you just run a control simulation, there's heat accumulating, ad infinitum if you don't put forcing.
These passive heat experiments is a control simulation effectively, because it's a passive tracer that's being added.
Yeah.
And if you add the heat like this, because it's a passive tracer, it's not causing any temperature change in a climate forced way, but you see it's still taken up at high latitudes. And the FATMF experiments show that Southern Ocean heat uptake is not really affected. There isn't really an ocean response to the fact that it's warming up. The ocean heat transports don't really respond strongly to that. So it is more or less like a passive tracer.
Okay, thank you.
Okay, thanks, Jonathan. I think we're gonna have to move on in the interest of time, but there's a lot of interesting questions in the chat. So
fine,
it'd be great
okay.
if you could have a look at that.
I will have a look, and also people, of course, are welcome to write emails to me. I'll try and answer. Thanks.
Hey, Jonathan. Our next speaker is Spencer Hill. He's an associate research scholar at Princeton University, and he's going to be discussing the symmetric and antisymmetric components of polar amplification. So Spencer, when you get a chance, you can share your screen. Okay.
Great. Okay, yeah, thank you all very much for attending. Be grateful for feedback and questions, especially if it's skepticism. This is sort of an unconventional approach to polar amplification. And it's also technically orthogonal to the ECS symposium title, because we're basically normalizing everything by the mean warming, but hopefully still of interest. This is work with Natalie Burles at George Mason, Tim Merlis, who like me has recently returned to Princeton, and Alexei Fedorov at Yale. So climatologically, zonal mean surface air temperatures are nearly symmetric about the equator. In other words, the decrease in temperature from low to high latitudes is much larger than the difference between either pole. You can see this in a CESM pre-industrial simulation here. The purple curve is the full annual mean surface temperature. The blue dash is the hemispherically symmetric component thereof, which is just the average of each latitude with its mirror about the equator. And the red dash is the mean plus the antisymmetric component. And the point is that the purple and the blue are mostly very similar to one another. That is true in the climatology, but the transient response to CO2 increase starts out quite antisymmetric. I'm showing now on the same model from years 1 through 10, all the way up to 3,000 years into the integration in increasingly dark colors, the anomaly in surface air temperature. And as this audience mostly knows, surely, we have Southern Ocean upwelling that slows warming initially, and you have rapid Arctic warming, but the Antarctic sort of gradually catches up to some extent, at least, over subsequent centuries and millennia towards equilibrium. So initially largely antisymmetric response. So intuitively, it's not obvious that the symmetric component of warming in the initial period, say the first decade or so, has much to do or encodes much information about the symmetric warming near equilibrium on millennial timescales. But that is precisely what we are going to argue here. So we're using 1,000-year or longer abrupt CO2 quadrupling simulations in CESM1, as shown already, and 11 models from the long run MIP archive to argue the following. Mean normalized, so normalized by the global mean warming at any given time, the symmetric component of zonal mean surface warming changes weakly or becomes modestly more polar amplified in all models. To understand the mechanisms underlying this robust response, we use a moist energy balance model applied to CESM1, which replicates the model behavior, and through perturbation simulation suggests that it's the sort of quasi-consistency of the pattern of the radiative feedback parameter in this GCM that is key to this consistency of the symmetric warming pattern. And finally, if we have time, I have too much material, so I might skip this. When we look instead at the model non-robust response in the antisymmetric component weakening amount, largely that seems due to major discrepancies in the fast warming timescale in the Antarctic. So if we're going further, just one might ask, who hasn't thought about this decomposition before, why would any of this matter? It matters because if you take at face value that the warming pattern, the symmetric component changes weakly, it implies that you can infer a great deal about the near equilibrium warming pattern in polar amplification from only a decade or so of simulation. Okay, so now I'm showing you mean normalized warming patterns in the same CESM1 quadrupling simulation from before. In the left is the full response. The middle is the symmetric component thereof. The right is the antisymmetric. The colors, again, are light to dark, increasing in time, and you can ignore all the numbers. I won't go to that level of detail. So the full pattern on the left, you see there's large discrepancies in the mean normalized pattern in the Southern Ocean and the Arctic, but they collapse much more towards a single curve when you look at just the symmetric component, the middle panel here. And that is in contrast to the antisymmetric component on the right, which gradually weakens nearly towards zero by the time you're at near equilibrium. Showing the exact same thing, but for ECM 5 from long run MIP, one of the other models we looked at, and it's a very similar behavior. Some spread in the full, very little in the symmetric, and more in the antisymmetric. And in this, as in CESM, by eye, you can see, and if you quantify, you can confirm that there's a slight increase in polar amplification in time, sort of to next order after the overall consistency. And then one last model, I won't show you all 12, but this is the famous GCM, which is something of an outlier. It too has a consistency of its symmetric warming pattern, but its antisymmetric warming pattern actually reduces like all the models, but only much less, by a factor of something like a third, as opposed to essentially vanishing in time. And these behaviors are robust across all 12 of the GCMs we analyzed. Okay, so now we want to understand why this is happening. So we use a moist energy balance model, simple diffusive model that we all know and love. This was Tim Merlis's biggest contribution here. What we do is we prescribe the model, the energy balance model, with radiative feedback parameter and ocean heat uptake fields diagnosed from the CESM1 simulation from these 4 different time periods we're looking at, as well as a realistic estimate of the radiative forcing. And these panels are the raw warming pattern and the mean normalized symmetric warming pattern in the GCM in red and the EBM in purple. And the point is that the EBM captures the GCM behavior suitably well in our estimation, such that we can then use the EBM further experiments to get at what's the underlying mechanisms. I think someone's unmuted on accident. Okay, so the first thing we do is we crank up the antisymmetry of the ocean heat uptake and lambda fields. And the punchline there is that it doesn't really have much of an effect. So comparing the yellow and blue curves essentially in these panels. The full pattern is strongly modified if you jack up the antisymmetry, but even then the symmetric component of the warming doesn't change all that much. So the symmetric component of OHU and lambda are what must be driving the behavior here. So we then, starting with the symmetrized versions of simulations in the red curves here, we then make one or the other of lambda or the ocean heat uptake uniform for the different timescales, but maintaining its global mean. And now we're only showing in dotted the first decade and the solid, the sort of 3,000 year timescale responses. The red and yellow curves go together and the blue and purple curves are a separate pair. The red is the sort of full case, as I mentioned, and the yellow is the case where ocean heat uptake has been made uniform. And so in other words, the ocean heat uptake spatial pattern doesn't have as much effect as the spatial pattern of the radiative feedback parameter lambda. So the blue curves are well separated from the red and yellow. In other words, the extent to which the symmetric warming pattern doesn't change much in time, that occurs to the extent to which the lambda pattern itself doesn't change so much in time. And so what is the ocean heat uptake, the lambda field doing in time? I'm showing you here. So again, full symmetric and antisymmetric from left to right. And these are the diagnosed lambda fields from the 4 time periods from the CESM1 4 times CO2 simulation. And the big behavior to note is going in the first decade, you have this strongly stabilizing global max, global extremum in lambda over the Southern Ocean. But by the next time period, over the next century or so, that decreases, that essentially vanishes. And so that does 2 things. It makes your lambda and the global mean less stabilizing, which increases mean warming, but it also makes the high latitudes less stabilizing relative to the tropics, which promotes polar amplification. Timing wise, yeah, very briefly. So we take Isaac's 2010 sort of 2 timescale fast slow response box model, and we fit it to 2 of the GCM, CESM, and FAMOUS, applying it separately to the Arctic, Antarctic, and lower latitude boxes. And what you find is that in CESM1, you get what you would expect. The fast Antarctic timescale is order century and much faster than the low latitude or Arctic timescales. As these time series, you can see, hopefully that comes out clear in the time series shown. FAMOUS is odd. Its Antarctic timescale is something like a decade, and it's not any different than the rest of the globe. So you can see the 3 curves for FAMOUS all are evolving over the same timescale. They just have different magnitudes. So that's why in FAMOUS, the antisymmetric component weakens much less in time. Okay, to recap, we are arguing that the symmetric mean normalized warming pattern changes weakly or becomes modestly more polar amplified in the 12 GCMs we looked at. A moist EBM replicates the behaviors in one model and suggests that a quasi-consistency of the lambda spatial pattern is key there. And at least one of the models is pretty funky in the Antarctic with its fast warming timescale. Okay, 2 closing slides. First, why might you be skeptical of this sort of non-conventional decomposition? One, it's meaningful physically only if the mirror latitudes feel one another. If they're independent, it's just convolving 2 separate signals. But we would argue that they do feel one another through perturbed atmospheric energy transports. There's a robust literature on that. Another concern is that this is just a complicated way of saying that the Arctic warms fast and then the Antarctic catches up. Those things do happen, but that in itself doesn't get you the latitude by latitude consistency of the symmetric warming component that we have found, right? Okay, bracketing any skepticism you still have, what we would be interested in doing next. The ultimate motivation here is this relevant for Earth's real climate? Can we ultimately say something from a short instrumental record about equilibrium scale responses? In addition to the vast complexity or much more complexity of the real world, you were looking at gradual forcings of different magnitudes, and non-uniform forcings in the paleoclimate and global warming scenarios. For non-abrupt forcing, a useful next step would be looking at naturally gradual CO2 increase simulations. Relevant for the forcing magnitude are simulations I didn't show of Natalie's, where it's a 2, 4, 8, or 16 times CO2. And the same behaviors and actually a sort of quasi CO2 independent pattern also emerges there. And then relevant for non-uniform forcings in Natalie's Pliocene-like simulation in the same model, by construction, the pattern is much more polar amplified, but it's also very stable in time. So the manuscript we've revised a couple times for Journal of Climate. The newest version is up on my website as of yesterday, and more so than usual, the reviewers were immensely helpful in pointing out some sort of inconsistencies or problems early on. So thanks to them, and thank you all.
Awesome, thanks, Spencer. Okay, while people think of questions, I'll ask, have you looked at this at all in observations? Like if you took, observed warming from like reanalysis data and you split it into a symmetric and antisymmetric component, do you see anything similar?
No, that is certainly something I am keen to do eventually. There's with the gradual forcing, there's much more internal variability to contend with. There is, the radiative forcing itself isn't well constrained. It's a much more complicated problem. I want to eventually go there, but I think first we're still doing a bit of due diligence, so to speak, to convince ourselves that this is physically real in principle, right?
Okay, great. I guess we should move on. We're maybe a little bit behind schedule, but please keep an eye on the chat, Spencer, as people start posting questions.
Yep.
Thanks so much. Our final speaker is Xiyue Zhang, an assistant research scientist at Johns Hopkins University. She will be discussing the remote impact of observed Southern Ocean surface warming and cooling. So I'd like to take it away.
Can you see the slide?
Yep.
Yes.
If you go back. Yeah, thank you for the opportunity. So today I'm going to talk about the work that I started as a postdoc at NCAR, looking at the remote impact of observed Southern Ocean SST trends. And this was really inspired or motivated by observations. So it's going to be less theoretical than the previous talks, but I'm going to start by showing the observed time series of SST anomalies for both the global mean and the Southern Ocean. So the global mean here is shown in black, and the Southern Ocean is showing green. And so despite global warming for the last 60, 70 years or so, the Southern Ocean actually displayed two different phases. So there's a warming phase that happened after or since 1950 to the end of 1970s, and then a cooling phase followed by that warming phase. And this variability of the Southern Ocean SST is often not captured by climate model simulations. And before talking more about simulations, I'm just going to show you a bit more backgrounds in why I think these trends are real, because we know Southern Ocean tend to have sparse data coverage. And to convince you that there are actually two distinct phases since 1950s, first I will show you a time series of data coverage over the Southern Ocean. This is from a paper by Fan et al. 2014. And these are all in situ observations over the Southern Ocean. So either ship or buoy data. And we can see that before 1950, we have very limited coverage. So the units on the y-axis is percentage for almost all seasons. And then we actually have a huge increase after around 1945. And since then, we have more than 50% data coverage in austral summer over the Southern Ocean. So we definitely have increased the coverage to be able to tell us something about the trends over the Southern Ocean. And if we look at the two different periods that I highlighted earlier, Fan et al. Also compared the SST trends to station, so land station surface air temperature trends, and they often match quite well. So the left map, the colors in the back are showing the SST trends. That's the warming phase. And the circles here are highlighting the land station surface air temperature trends. So often they match quite well, and especially over the Antarctic coast during this earlier phase, it's consistently showing warming, whereas if you look at the later phase, it's mostly showing cooling. And the zonal mean actually has opposite trends once you are south of around 40 degrees. So hopefully I've convinced you that there were these two distinct periods in the Southern Ocean SST. And we also know from idealized experiments that if you have a strong forcing over the extratropics, you can have a tropical response. So this is just one of these idealized studies that imposed a negative southern extratropical forcing at the top of the atmosphere. This is the ATOMIMP experiment by Kang et al. 2019. And what they found is that at the equilibrium, the SST, we see a negative, so a cooling over the tropical Eastern Pacific that is a result of this negative forcing over the southern extratropics. And this is a really robust response. Almost all models show a negative SST anomaly over the tropics. And so this made us think that potentially the observed variability over the Southern Ocean can have a tropical impact. So first I'm going to go over quickly the Southern Ocean cooling phase. So this study has been published in GRL, and I'm going to introduce the experiments that how we were able to include the observed Southern Ocean variability in a couple climate model. So the method that we use is called a pacemaker experiment. And what we did was to nudge the Southern Ocean SST anomalies in CSM1, a coupled climate model, to the observed monthly SST anomalies. And we run 20 different ensemble members under historical and RCP 8.5 relative forcing. So we have these SO-PACE ensemble, and what we can do is to compare that to the large ensemble of CSM1, which has 40 members. And in that way, we can separate the radiatively forced response, which is represented by the ensemble mean of large ensemble lengths, and the internally forced response, which we call SO-PACE internal. So Note that I haven't discussed the origin of the Southern Ocean variability, and that is outside of the scope of our study. But there are reasons for us to believe that the variability is internal in nature. So if we look at the ensemble mean results from our simulation, on the right, we have 3 different panels. The first panel is showing the ensemble mean of SO pace. So this is the ensemble mean of the pacemaker run, where we nudge the Southern Ocean SST to observed anomalies. So they're very comparable over the Southern Ocean. But outside of that region, SSTs are freely evolving, and we see some some cooling that is not significant in the tropical, the Southeastern Pacific, as well as some muted warming in the tropical Atlantic. And a lot of these tropical Pacific response actually comes from the radiatively forced component, which is shown in the middle. So this is the ensemble mean of the large ensemble. And this pattern actually emerges in a lot of climate model simulation of increasing CO2. So if we subtract the radiatively forced response, we actually get the last panel, which shows the response to just the Southern Ocean cooling. And there, the most robust response we see here is actually over the tropical South Atlantic. So it's statistically more significant than what we have in the tropical Pacific, which is really weak. So of course, we don't expect the ensemble mean to match observations because ensemble mean doesn't show the internal variabilities which the observations have. So one way to compare them is to look at the spread across the ensemble members. And the bottom line is that including the Southern Ocean cooling is giving us a better match with the observations, both for the tropical South Atlantic mean SST trend. So here the gray line is representing observations. So the distribution of SO pace is shifted further or closer to the observations than the large ensemble. And another way is to look at the pattern correlation of the greater tropical Atlantic region. And again, the SO pace ensemble has higher pattern correlation, especially between observations and the ensemble mean of the SO pace, which is represented by the triangle. It's a shift from about 0.2 to now more than 0.6. So both metrics show that there's improved simulation of the tropical Atlantic SST pattern. So that was from the Southern Ocean cooling phase. What's new here is I'm going to show you some preliminary results where we also simulated the earlier phase where the Southern Ocean warmed. And if you look at the pattern, it does correspond to a weak tropical warming over the Pacific, as well as some pretty significant warming over the tropical South Atlantic. So, so that is something that we're expecting to see from our experiments, but also to boost the signal of Southern Ocean SST forcing, we calculate the difference in SST trends between the 2 periods. So that's shown on the right. So if we do the warming minus the cooling phases, we get the map where we have a very strong warming over the Southern Ocean, accompanied by warming in the tropical South Atlantic and tropical Eastern Pacific. So first, I will show you the ensemble mean of the Southern Ocean pacemaker for each period, as well as the difference. Not surprisingly, we do see warming that is connected to the Southern Ocean warming in the earlier phase, and in both the Pacific and the Atlantic basins. And if we calculate the difference, we get the panel on the right. So remind you that these ensemble mean actually includes the radiatively forced response. So that pattern is kind of making it harder to compare with observations. So one way to look at, I guess a more realistic way to compare to observations is to look at the individual ensemble members. So one way to do this is to look at their spread in the SST trend difference of the two periods. So I'll focus on two regions. First one is the tropical South Atlantic, which I focused on earlier for the cooling phase. And if we calculate the average SST trends for the two periods and calculate their difference, we can actually do that for each ensemble members. And we can compare the large ensemble, which is shown in blue, and the SO pace, so the Southern Ocean pacemaker in orange. And I'm showing the comparison for the annual mean as well as each season. So now observation is shown star. And what is very cool to me is that if we just look at the large ensemble, the star is almost always outside of the spread of the large ensemble. But once you include the Southern Ocean, observed Southern Ocean trends, you're able to move the distribution to always include the observed value for all seasons. So that is something quite significant and robust over the tropical South Atlantic. On the other hand, for the tropical Eastern Pacific, we only see that same signal in certain seasons. In DJF and SON, before the large ensemble can't really capture the observed values, but now we can after including the Southern Ocean SST trends. And it's not the case for the other seasons, but there is definitely, in general, a shift of the distribution towards the observed values. So just a quick teaser, we just started to look at the different processes that may contribute to the tropical response, and clouds are one of them. And I have just calculated the liquid water path trends in the pacemaker simulations, and also their shortwave cloud radiative effect trends at the surface. And both are consistent in that when you look at the difference between the periods, because the Southern Ocean has warmed, we actually see a decrease of low clouds over the coastal regions of Africa and South America, where we have climatological high cloud amount. And this decrease actually corresponds to a positive anomaly or trend in the shortwave cloud radiative effect. So the clouds here definitely contribute to the local SST changes. So just to summarize, the inclusion of the observed Southern Ocean SST trends in CSM1 leads to more realistic tropical South Atlantic and tropical Eastern Pacific SST trends. And I'm going to end with this plot that I really like. I'm showing the significant improvement of tropical South Atlantic SST simulations in the pacemaker. And I'm happy to take questions. Also, please feel free to contact me if you have further questions.
Awesome, great talk, Sally, really clear. Are there any questions? Maybe I'll kick it off by saying it seems like even in these pacemaker experiments, the observed trends are still kind of on the edge of the internal variability simulated by the model. Is that right?
Yes. Yeah, it does seem like it's often on the edge, or only the outlier captures the observed values. And I think we know that especially this region, the model definitely has bias in the SST, in the simulated SST. So potentially that's also shown here, that the observation can only be captured by the outliers.
Yue, would you like to unmute yourself and ask your question?
Yeah, sure. Can you hear me?
Yes.
Yep.
Hey, Sally. Yeah, very cool results. I just wondered because your cooling experiments shows no significant tropical response, but your warming simulation and the combination of these two suggests a pretty significant tropical response. So does it suggest that the teleconnection, at least in this model, is sort of sensitive to the amplitudes of your Southern Ocean SST forcing? And if so, what is the mechanism? Do you think it's the same mechanism in the cooling and warming scenarios?
Yeah, that's a good question. I haven't done detailed analysis of the ocean mixed layer budget to see if the response is exactly the same for the two phases. But I think, yeah, you're right that I think the amplitude might be a bigger contributor to the differences between the two periods, because they're definitely not exactly opposite for the cooling and warming. So also the significance in the tropical Eastern Pacific really shows up once I calculate the difference between the periods. So that's definitely when the forcing is stronger, we get a more significant response there. So I think the magnitude of the forcing matters here.
So you
but
think
I don't have.
Oh, sorry.
Yeah, go ahead.
Sorry. Yeah, I just wonder why there isn't a significant response in the tropics in response to the Southern Ocean cooling. So you think that's simply because the Southern Ocean cooling signal is small to generate a significant teleconnection to the tropics?
Yeah, I think it is weaker because when we do the difference of the two periods, you're basically doubling the forcing. So given the amount of natural variability over the tropical Eastern Pacific, I'm not surprised that when you have stronger forcing, you're more likely to bring out the signal to be significant.
Okay, yeah, thanks. Very cool
Thank
results.
Anyone else? Okay, if not, well, you can end a couple minutes early. And thanks again a lot to all three speakers for a really great set of talks. And again, please get in touch with us if you'd like to give a talk in the future. Bye.
Thank you for organizing.